viewing the lesson and seeing it's your last new lesson in pre-calculus. I realize that it's a sad moment, and that there'll be a lot of memories attached to it someday. But I'm sure that there'll be other math classes that make you forget this one. There's always another math class. Just remember that. It's a hopeful thought, isn't it? There's always another math class. So, as we're doing this today, just remember that this is one of those lessons that's going to propel you on into another math class. Mathematical induction. I think it's important that you at least see this. It's not going to be a major portion of our test or anything, but it is something that gets used a lot in higher level mathematics. It's a method of proof for mathematics. Not the formal two-column proof that you learned in geometry, but more of a higher level proof that is done using equations and stuff. It is algebra heavy. We will definitely use a lot of very simple algebra, things like FOIL and polynomial addition and that sort of stuff. You'll see the process here in just a minute. But basically, this is what's done. It's a way to prove formulas for sums in mathematics. Because a lot of times they give a formula. We want to create a formula for the sum of a series that is not arithmetic or geometric. If we have an arithmetic series, I got a formula for the sum. It works. If I have geometric series, I've got a formula for the sum. We've got those formulas. We've been using them. But what happens when I get a series that's neither arithmetic nor geometric? Sometimes, how do we prove the sum is actually valid? And actually, we can prove this for arithmetic and geometric ones as well. So it can work both ways. Basically, the way it works is this. It says show the formula is valid for the first case, usually when n equals 1. Assume the formula is valid for the kth case, for n equals k, and prove the formula must be valid for n equals k plus 1. And the way we do that is by doing two equations and showing that they have to be equal. And I'll show you how we do that with numbers here right away. It says prove that the sum, and this is actually an arithmetic one, so it's not so bad. For 1 plus 4 plus 7 plus etc. plus the terms of the sequence are defined by the formula 3n minus 2 equals n times 3n minus 1 divided by 2. Okay? So that is what we're going to try to prove. We're going to try to prove that that formula is valid. Well, the first thing we do in induction is show that it's true for n equals 1. Well, when n equals 1, 1 times 3 plus 1 minus 1 divided by 2, 3 times 1 minus 1, excuse me. Yeah, 3 times 1 minus 1 divided by 2 equals 1. 3 minus 1 is 2 times 2 over 2, which is 1. So that means the sum after one term needs to be 1, which it actually is because the first term is 1, right? So the sum of one terms of that sequence is 1, which is exactly what it should be since the first term is 1. Okay? That's usually pretty simple. Assume that it's true for n equals k. This is great. I love this part because we get to assume something. We don't have to prove it. No math involved. Okay? Now comes the fun part. Prove that it is true for the term n equals k. And I refer to my notes just to make sure I do this properly. I actually took notes. Because I just created this lesson like 5 minutes ago. Woohoo! I didn't have one. I thought I had one for this. I didn't. So I always want to make sure I get it right. So the way we do this is we say, okay, what happens if I just have, if this is my sum for n terms, or for k terms, what would my sum be for k plus 1 terms? Well, the next term in the sequence, 3n minus 2, the next term would be 3k plus 1, because we're adding 3 each time, right? Okay? So the next term in the sequence, if my rule is to add 3 each time, the next term on this would be 3k plus 1. if I did the next term, or 3n plus 1. That'd be the next term after this one, because we're adding 3 each time, right? That's always a little bit tricky to figure out what the next term is going to be, but that's okay. So for the k plus 1 term, we'd say the sum of that would be this, n, or k, times 3k minus 1 over 2 plus the next term, 3k plus 1. And then we algebraically combine those terms. So that's going to be 3k squared plus k over 2 plus 3k plus 1. I need a common denominator, so I got to multiply top and bottom by 2 here. So that's 3k squared plus k plus 6k plus 2 over 2. Or 3k squared plus 7k plus 2 over 2. So that'd be sum of the k plus 1 terms if I just added my next term to it. What then I do is I juxtapose that, or I compare that to what would happen if I just put k plus 1 in for n. Because we're going to increase n by 1. So we're going to put k plus 1 in for n. Well, then we get the formula, since n, now what happens when n equals k plus 1? Well, that would be k plus 1 times 3 k plus 1 minus 1 over 2. I simplify that. K plus 1, this is 3k plus 3 minus 1, so that's 3k plus 2. Over 2. Then I FOIL this out. 3k squared plus 2k plus 3k wait a minute. That should work out. Hold on, let me check notes. This is supposed to be a 5 when I check my notes. That's okay. We'll get it in a second. That gives me plus 5k plus 2 over 2. Now, these should be equal. I realize they aren't, so I can go back and look. This is the one I made a mistake on. Where did I make my mistake simplifying that? 3k plus k, 3k plus 1 times 2, 6k. Did I lose a minus sign? Hold on, let me check where I did. This is why I did this ahead of time, so I'd avoid this. Minus k. Yes, this is, oh, there, I lost the minus sign right there. That's what I did. Minus k. There's my 5k. There we go. Sorry, I just didn't distribute a minus sign. And we get them the same on both sides. And that's how we do the induction proof. Basically, we solve it twice. One is if it's just the formula plus the next term. One is if we substitute k plus 1 into the formula. Okay, that was a little bit weird. Let's do another one. For the second step, you don't do anything. You're just assuming that it's true for n equals k. So you make an assumption. And it's allowed to do that. Here's a formula for sum of squares. 1 squared plus 2 squared plus 3 squared, etc., plus n squared equals n times n plus 1 times 2n plus 1 over 6. Let's prove that that's true. So step 1, show that it's true for n equals 1. So for an n equals 1, we get 1 times 1 plus 1 times 2 times 1 plus 1, excuse me, extra parentheses, plus 1, over 6 equals 1. Well, that's 1 times 2 times 3 over 6 equals 6 over 6, which is indeed 1. So I've just proven that it's true when n equals 1. I substituted 1 into the formula and showed that the sum of one term is exactly 1 squared, which is 1. Yay. It seems kind of trivial, but it's what we need to do. Second, I assume it's true for n equals k. Okay, so the sum after k terms would be k times k plus 1 times 2k plus 1. So what would my show it's true for? Okay. Yeah, I have to extend the page. I know that right away. So what would the k plus 1 term look like? We got to figure out both ways of expressing the k plus 1 term. One way we're going to express it is this with k, so k times k plus 1 times 2k plus 1 over 6 plus my next term, which would be k plus 1 squared, right? The next term, if I was to take the next term, add another term to this, instead of having n and there k, having it in a k plus 1, I'd add a k plus 1 squared. And now we simplify that. Now that's going to take a little bit of algebra work. Hint, don't distribute first, FOIL these two first, because that's a little bit easier. It's less multiplication. So when I FOIL these two, I get 2k squared. So I get k times 2k squared plus k plus 2k plus 1 over 6 plus k plus 1 squared, which is k squared plus 2k plus 1. Okay, simplifying this, combining terms, that gives me a 3k, that gives me 2k cubed. This is 3k times k is 3k squared. Just 1 times k is plus a k over 6 plus k squared plus 2k plus 1. All we're doing right now is just algebra, combining terms and that sort of thing. Okay. I need to get a common denominator over here, so I'm going to multiply by 6 over 6 to get a common denominator. So that gives me 2k cubed plus 3k squared plus k, multiplying this by 6, that gives me another 6k squared plus 12k plus 6 all over 6. And then combining like terms, I get 2k cubed. 3k squared and 6k squared is 9k squared. 12k and 1k is 13k plus 6 over 6. Okay? So there we've simplified that about as much as we can. The other side of the proof is, okay, that's what happened when I just added one more term to the existing sum. The other side is, what if I run the sum with a k plus 1 instead of an n? So if I run the sum with a k plus 1 instead of an n, I get a k plus 1 times k plus 1 plus 1 plus 2k plus 1 plus 1 times 2k plus 1 plus 1 all over 6. So I substitute k plus 1 wherever there was an n. Now I'm going to simplify that and see if it equals the same thing. It better. So this is k plus 1 times k plus 2. That's 2k plus 2 plus 1. That's 2k plus 3 over 6. It's a little more just FOIL at this point. K plus 1 times k plus 2 is k squared plus 3k plus 2 times 2k plus 3. And if I multiply this out over 6, multiplying this out, I get 2k cubed. K squared plus 3 is 3k squared plus 5k squared is plus 9k squared. To get my k terms, I'm going to get 3k times 3 is 9k. 2 times 2k is 4k, so that's 13k. My last term is 2 plus 3, or plus 6, over 6. Aha, they're the same. Proven. That's our process. It's heavy algebra. Heavy multiplying polynomials. As you saw in the first example, I dropped a negative sign, changed to a plus sign. Oops, I messed everything up. I was so close, so I knew I'd made a simple mistake. So it was easy to find. But that is our process of mathematical induction. You have like 5 whole problems of this to do tonight. That's your assignment to practice this. All right? That's your whole assignment. We're on page, and that's it. That's the last new lecture. And this is the last assignment. I know. Don't cry. Don't cry. Don't cry. So 9, 10, 11, 13, and 15. 13 and 15, of course, I believe the solutions are in back. If you get stuck, I mean, basically 10 is the only even problem. The rest of them are all pretty actually well laid. If you get stuck, they're pretty well laid out in the back. So at least 11 and 13 are. 9 is also. So 9, 11, 13, and 15 are all pretty well laid out in the back. If you get stuck, don't be afraid to use that as a reference. 10 is the only one that you're really completely on your own on. So you're only on your own in one problem here. Just a quick note on the final in here, just so you're aware. This final is about 50 questions that are multiple choice and choose the greater of the 2 columns type thing. It's kind of an ACT, SAT style exam. Okay. Some of the questions we're going to see on the final are going to look a little bit different than maybe what you're used to seeing on a Milton High School math test, but you will see it a lot in other types of math tests. And so let me just kind of very quickly go over what that is going to be. They're going to be a series of questions that say, multiple choice still, A, if column A is greater, B, if column B is greater, C, if the columns are equal, D, if it cannot be determined. Okay, That's the instructions. Those are your multiple choice answers. It's been naughty. And then what they'll do is they'll have something like this. Okay, here's the problem. X equals 3. Here's column A. Here's column B. And you just solve for it and decide which one is bigger. Now, that's, of course, a very simplified version. I mean, it might be things like something like the complex portion of okay. So obviously in something like this, you'd have to convert this into just a plain complex number so you could compare their complex portions. Portion of. So the complex number, the complex portion, not the real, but the complex. You couldn't compare. Greater than, less than kind of loses its meaning with complex numbers. I mean, is 7 plus 2i greater than or less than negative 3 minus 8i? I don't know. No, like about maybe 25 to 30% of the problems are going to be like that. Are going to be like, choose column A, column B, are they equal or neither? The rest of it's more straight up multiple choice. Which is the correct graph for, you know, y is greater than or equal to x squared plus 2x plus 7 or something like that. This semester. It is a semester exam. It's just over material from this book. Yes, the review packet, however, is not multiple choice. So, just so you know. Yes, I printed off my first copy of that, and I'm double checking it today. So I'm hopefully going to get it copied off and available for you tomorrow. But tomorrow we will actually be reviewing for the chapter test first. I mean, I'll give you the review packet tomorrow, but the chapter test. Because this exam technically is not until, since this is our last exam, it's our final. Yay! For some of you, it's the final. The final. For you seniors. I know, don't cry. I know you're excited that at least your last experience in high school gets to be mathematics. I'd be excited about that. But I will probably at least one day during the flex time, like just be here for a review for just pre-calc. Probably that second flex day after flex, because I don't think I have any, because I don't have any geometry tests left to do after that. You're my only exam that last day. So, learning lab. So second hour is prep, so you're my only exam that last day. I'm just waiting for you guys with bated breath. So that second flex day, Wednesday afternoon, it'll be purely pre-calc for people who want to come in for work on that. Okay? Any questions? So what we have left, review tomorrow, chapter test Friday, review Monday, nothing Tuesday, flex period Wednesday if you want to be here, your choice. Thursday exam, Friday graduation practice. Saturday, try not to get arrested. Sunday graduation. And yes, that's on the podcast.